All right, so the last of the videos on energy will really be the last of the videos that we focus on primarily conservation laws. And the goal of this lecture is to see that conservation laws do not have to be applied obviously individually. There are cases where you can use multiple kinds of conservation laws together. And so this lecture will more or less be 3 examples of using multiple conservation laws or Newton's laws with a conservation law. Everything we've been talking about up to this point, right? It's not that they always appear only one at a time, but you might want to mix them up. Use momentum and energy conservation. Do radial motion, polar coordinates with energy conservation, something along those lines. So let's remind ourselves of the 3 big conservation laws that we've talked about. The first is momentum. The total momentum, all the m times v times v's of the system, that if you add up for that particular system, that system's momentum can only change if there are net external forces acting on the system. If there is no net external force, or if a component of the external forces, like say only the x direction or only the z direction, right? And I'll just do it as a vector. If x net equals 0, then momentum is a constant vector. Which might be true only for a component of the momentum, right? If it's the case where there's no net external force in the horizontal direction, but there's gravity and normal forces and things in the vertical direction, then maybe you can say that the horizontal momentum is conserved overall, or something like that. And remember, we said things like you can usually apply this or approximate the external forces as being 0 in the case of collisions where things are happening really quickly, and external forces, while they might be present, won't have enough time to really change the overall momentum of the system. So you can look at 2 snapshots that might be very, very close in time. Or if you know that momentum is conserved more generally, you might be able to apply it to 2 spots that are very much disconnected in time. Remember, this also led to a variety of other things. We were able to say something like that the center of mass of the system was related to the net external force all over the total mass of the system. So if the center of mass is going to accelerate at all, this is what we said was Newton's 2.5 law, because it combined Newton's second and third law for point particles, where the center of mass of a system accelerates from net external forces, even when there's relative motion going on internal to the system. And so again, if we take that a little further, if momentum is conserved, well, that's the same thing as saying, right, if momentum is conserved, then that's the same thing as saying that there's no net external force. It looks like by the equation right above, that implies that the center of mass has no acceleration. So then that implies that the velocity of the center of mass is going to be a constant. Particularly if it's 0, if the center of mass is initially stationary, it remains stationary. And there are problems you can think of, like planets and moons going around each other. They're all orbiting around their common center of mass. But if that's the system, then while there's all this relative motion going on, the center of mass of that solar system is stationary, unless there are external forces tugging on what's on your system. Similarly, we said something with angular momentum as well. Angular momentum is conserved not when there's no net external force, but when there's no net external torque. And again, remember that angular momentum has that special property, and torques also, where the magnitude of the angular momentum and torque is dependent on your coordinate system. It depends on where you define your origin. So you can get different values and might say whether things are conserved or not in different coordinate systems depending on where you put your origin. Typically then you choose your origin to be, ideally, where pesky forces you don't know vanish, or their resulting torques vanish, or maybe you can put your coordinate system in such a way where you might be able to say that in that particular coordinate system, from that reference point, there is a conservation that's obeyed with momentum, angular momentum. So we can write down, we can remind ourselves, right, that this is dependent on choice of origin. And then finally, we've been talking a lot about energy, how you can always start with that the change in kinetic energy is the result of work being done on an object. So if I want to think of it like a time derivative so that there's some parallelism with the statements I've written down, you can think that the time derivative of kinetic energy is the time derivative of the work that's being done on the object. Usually instead we think of it as that delta t is the result of net work being done on the object. Which might be, if there's multiple forces, it might be the net work from conservative forces plus the net work that's being done from non-conservative forces. That is a general statement, where I've additionally identified that there are particular forces where we can call them conservative forces. Remember, F is conservative if, and we had a test, if the curl of that force equals 0. In that case, then that is a conservative force. If it's a excuse me, if it's a conservative force, then F can be written as negative the gradient of some function that we call the potential energy, such that the change in potential energy is equal to negative the work that's done by that conservative force. And that negative sign flying around is, again, a physics convention, so that we can write it down. We can write conservation of energy down in a way that seems reasonable. Because then the net conservative force, or the work being done by the net conservative force, is then negative the change in potential energy from conservative forces, and then there's plus the net work being done by non-conservative forces, and I'll drop the nets. So then, of course, you can move the delta U to the other side, and it looks like the change in kinetic plus potential is equal to the work being done by non-conservative forces. And that might be viewed as kind of an upgraded version of the work energy theorem, because it's still the work energy theorem, but I've allowed that some of the forces might be conservative forces, so I know I can associate those forces with a potential energy function. And so then, if we call this thing on the right-hand side, or on the left-hand side, the total energy E, then E is conserved when there is no work being done by non-conservative forces. When non-conservative forces do no work. It doesn't mean they can't be present. There can be, for example, a box going down a ramp. When the box is going down the ramp and it's frictionless, there is a normal component pointing up from the ramp, but it's pointing perpendicular to the direction the box is moving as it moves down the ramp. So while there is a non-conservative force acting on the box, it's never doing any work in that case. So you can still say, if it's only gravity and the normal component of the ramp, energy is still conserved for that box as it goes down the ramp, for example. And then we also had a couple examples of potential energy functions, right? We had potential energy function of a uniform gravitational field, which we wrote as mg, it might be something like y, or if we have some arbitrary reference point, mg y minus y naught, where this is the reference point. We had things like a spring, which is 1/2 k. Then I might write it as s minus s naught all squared, where the s is just the overall displacement, right? You could put an axis along the direction of the spring, like put the spring along the x-axis, then it becomes x minus x naught. But it's just, right, it's whatever kind of amount of stretch is going on. And this might be kind of where the spring is neither stretched nor compressed. And notice that's also where, in this way that I've written down, that's also the location where I've defined my reference point, because when s equals s naught, the potential energy is overall 0. And then for Newton's universal law of gravitation, we had, again for gravity, it's usually something like G, big M, little m over R. Where in this case, the reference point is r equals infinity. Because we can't let the origin be the reference point, because then we would be dividing by 0 in this case. So we have to put it somewhere else. The convention is usually to put it really, really far away from the object in question or the objects in question. So we call that r equals infinity. Where gravity, right, since gravity is an inverse square law, gets weaker and weaker and weaker and doesn't actually ever vanish until you go out to this hypothetical r equals infinity. But again, you can define your reference point to be whatever you want it to be, and then there would be more or less an overall constant that's being added to any of these potential energy functions. But since it's only changes in potential energy that have any meaning, again, go back up to the highlighted equation, it's a delta U that relates to work or relates to changes in potential energy. So again, if you have an arbitrary constant being added to any of these potential energy functions, who cares? Because the changes will get rid of those constants. Though again, sometimes it's useful making your reference point a particular point of interest in the problem. Because it's always nice when you're solving problems and you get to plug in 0 compared to plugging in something else. But again, you should ultimately get the same answer. All right, so let's see, question 1. The minimum height of a roller coaster. So suppose you have a roller coaster that starts, right, you're kind of ramped up to some height h, and then the roller coaster also has a vertical loop that has radius r. You're starting up here, you are excited, about to go over the edge, and you're some height h off the ground, but then there's a hoop that has radius r. And if you start from rest, or you're just kind of giving a very gentle nudge over the edge, what is the smallest value of h such that you make it over the hoop? This vertical hoop. And let's take the roller coaster to be frictionless, and that the hoop is a perfect circle. Now you might initially think that the value of h should be 2 times r, right? You might think h equals 2r is what you need. Because in that case, you would have something that looks like this. Right, this is r, and then this is also r. And you might reason, well, you might be thinking, okay, what's conserved? In this case, I expect energy to be conserved because while I am always in contact with the ramp, it is always, since there's no friction, right, if this is the ramp, you know, as I'm moving down the ramp is exerting a force, but it is perpendicular to the direction that I'm moving. So the coaster, or I'll say the coaster, does no work. Or the track does no work. Yeah, is the cart itself the coaster part? Maybe. Well, the track does no work. So then, but there's still gravity acting on the person. Gravity is a conservative force, however. Seems like there's only conservative forces doing work on the roller coaster, so you might expect then I can apply energy conservation. And with energy conservation, you might identify that if this is your starting point, at your starting point, the total energy, T plus U, looks like it's just going to be 0 plus mgh. And then at your end point, you might ask, if I'm going to make it over the hoop, then I should be able to at least get to the top of the hoop. But then notice at the top of the hoop, right, what is the total energy? Well, you go back to having mgh, and then you have to ask yourself, is it possible to have any sort of kinetic energy at that point? And since these are equal to one another, you have to realize that v has to equal 0. Right? Suppose it didn't, right? And you put 1/2 mv final squared at the top of this hoop. Well, then by energy conservation, it looks like mgh equals mgh plus 1/2 mv final squared. And you have to conclude then that v final better equal 0 if that's going to be true. Else you have some sort of contradiction about energy conservation. That is not what I would call a successful loop or a successful roller coaster ride. You would go down, you would come back to the top of the loop, and then you would get stuck. And if there's nothing holding the cart to the track, you would then just fall down, which would be a very bad day. That would not be a very exciting ride where you go over the loop fully. You would get to the top of the loop and then fall to your death. So that suggests that h should at least be a little bit higher than r. Because in that case, then you would have some kinetic energy that's left over when you got to the top of the loop. So you might think, well, it has to be anything that's greater than 2r. But that also can't be true. Let me see if I can try to do this. Right, if you had some, right, there's a difference where if I start here and I let it kind of, well, let me get shorter. If I start here and let it fall down, then by energy conservation, I should be able to make it over here. And so if I kind of start up here, I might be able to make it, over the top, right? If there's true energy conservation. And admittedly, I'm cheating a little bit, giving it a little tug with my hand. But you can imagine that if you're slowing down, I would not call it successful if you're going across the track, and imagine this thing is a big circle, and you do something like this. Where notice the ball is not moving in a circle the entire time. It kind of goes up and then just kind of plops, right? Goes up and then kind of goes bleh, rather than traversing in a full circle, which is what you want it to do if you're making it over the loop, right? Rather than it kind of making it partially over the loop and then plopping over. So in this case, you not only want it to be able to make it through the loop, but you want it to be able to make it through the loop while being able to retain circular motion. Which means without it kind of plopping down, right? It still might be able to make it to the top, but then it might immediately fall off or shortly thereafter fall off and not necessarily follow the circular track unless you had some other force on the cart, like some sort of brake or hook that is holding it on. But if we take the hypothetical roller coaster where there's nothing holding the cart onto the track, what height do you need so that you can complete the circle and still go on, right? You might have had toys like this as a kid, of a little like Hot Wheels or something that goes over a track. There's nothing holding the Hot Wheel to the track, but if it's going fast enough, it can make it over the hoop without it falling off. So in this case, we need to combine both energy conservation as well as doing a radial polar coordinate analysis, particularly of what's going on at the top of the loop. If it's retaining circular motion, we know what we can write down for the acceleration that the cart better be experiencing at the top of the loop. Right. In circular motion, which again, meaning that r is a constant. If I study this from the point of view of from the center of the loop, then remember we have the acceleration vector from the center of the loop. That's going to look like r double dot minus r theta dot squared, comma r theta double dot plus 2 theta r dot, theta dot. If we're constrained to move in a circle, or we're making ourselves so that we move in a circle, then those two cancel. We also know the velocity, if you're constrained to move in a circle, right, better look like r theta dot in this case, in the r direction, and r theta dot in the tangential direction. but nothing in the radial direction, because it's not getting farther or closer away to the center of the circle, but it is moving tangential to the circle. So then we know the acceleration, at least in the r direction, if I combine these two, you get the usual that this better be equal to v squared over r in the radial direction, negative v squared over r, where v in this case is just r theta dot, the magnitude of the velocity vector. And for uniform circular motion, remember for uniform circular motion, we said, well, v is a constant, r is a constant, this is all a constant as long as it points towards the center of the circle. For a vertical loop, however, you know if you've ever been on a roller coaster, your velocity is not constant. You're still constrained to move on a circle. So your radial acceleration better still be negative v squared over r, but that v is changing as you go, along the circle. So if we're going to stick with moving in a circle, we need to be able to we need to have enough velocity such that when we get to the top of the loop, we can still have this particular acceleration that I've written down and to maintain that acceleration without requiring that we lose contact with the cart, or with the track rather. So if we just do a force analysis of the loop, particularly at the top. So at the top, I could make my system the cart, and it looks like there are two forces acting on the roller coaster cart. There's gravity, and then there's also the force on the track from on the cart from the track. That is also pointing away from the track, so there's some normal component there, which is the contact force. Since there's no friction, it is the only contact force between the cart and the track. So then if the sum of the forces equals the mass of the cart times the acceleration of the cart, at least in the radial direction, I know, and again, towards the center of the circle is negative, away from the center of the circle is positive, that this looks like it's going to be negative mg minus the normal component from the contact, and that better equal the mass of the cart times the radial acceleration, which we just said is negative m v squared over r. So it looks like then, in order to maintain circular motion, at the top of the loop, the loop better be exerting a force that is equal to, looks like m v squared over r minus mg. If that is true, then circular motion is maintained. So circular motion requires this. But again, v is allowed to change. So you can just look at this equation and realize that there are cases where that might not necessarily be the case, right? If v is 0, then the normal force, let's see, let's be careful with our signs as well to make sure what we're doing is correct. Right, so I've already thrown in a minus sign here to kind of specify the direction of the normal force. So since I've already thrown a minus sign in there, I'm writing down capital N as if it's just some positive value, because I've already given some directionality with that negative sign. So I expect the normal force to be positive if it's pushing you towards the center of the circle, negative if something has gone awry, or maybe even 0, which would mean that you lose, right? It means that you lose contact. And you can imagine, you could easily solve what value of the velocity in this case would make the normal force vanish in that case. So you can imagine that not all velocities will work. There are velocities I could plug in here where the normal force would go negative, which means we've more than lost contact, or that the normal force goes to 0, which is right at the precipice of when it loses contact. So if I copy that over to the other page, is that, not highlighting, But we need this normal force, which I wrote as mv squared over r minus mg, to be greater than 0. So now we can try to tie this in, because we ultimately want to say something about how high that initial ramp needs to be. And we don't have h anywhere in here. But now we can loop in conservation of energy. So additionally, we know that energy is conserved. So at the top of the ramp, we know that you have mgh of potential energy, no kinetic energy. And at the top of the loop, you expect that you probably have some kinetic energy at that point. And you do have some potential energy as well, because you're 2 times r off the ground. We're not at the bottom, but we're at the top of the loop. So then this allows us to match that mgh better equal mg times 2r plus 1/2 mv squared. Looks like the m's will all cancel. And if I ultimately want to solve for v, it looks like I can multiply everything by 2. So I get 2gh minus 4, looks like gr equals v squared in that case. Or v squared, if I factor some stuff, looks like 2gh minus 2r at the end of the day. Okay, that's not too bad. So now we have an expression for v squared. Notice I didn't bother taking the square root, because the normal force in this case looks like it's m over r times v squared. So then I'll replace in 2g h over 2r. Then I subtract away mg, and I want that to be greater than 0 if I'm still going to be in contact with the track. So again, I can get rid of those m's, because there's technically a g all around, so I can get rid of the g's as well. So then it looks like it's, if I multiply the r in, it looks like it's 2 h over r minus 2 when I divide by r there. Minus 1 is greater than 0. Must be true. And it seems like we're more or less done. Looks like 2h over r minus 4 minus 1 must be greater than 0. Or that 2h over r minus 5 is greater than 0. Or that h over r is greater than 5 halves. Or that h is greater than 5 halves times r. That is the minimum height that you need in order, if you want to have any hope of making it over the loop and stay attached to the loop, your initial ramp better be 2.5 times the radius of the loop. So I've seen this called the roller coaster equation, but again, it's just polar coordinates plus energy conservation in this case. And notice, again, you can check yourself, when you plug in h equals 5 halves times r, that is the instance where you would find that the normal force vanishes. So that would be the part, that would be the height where you just barely make it over and you're just about to lose contact with the ramp, or with the track, in this case, the loop track. So as long as you're above that, you'll make it through the loop with ease and have enough kinetic energy to make it to the bottom and stick with the circle, rather than kind of coming up and then plopping over. Of course, real roller coasters have, you know, brakes and locks that hold you onto the track, right? Because sometimes, or it's intentional, that it wants you to kind of like hover at the top a little bit, and then there might be a little motor or something that pushes you, right? So it nudges you over that unstable equilibrium point and then has you go down. But if this were, right, the Tonka truck, you know, Hot Wheels, you know, roller coaster, it better be at least 5.5 times r. All right, that's one example. Now, what about, let's do one that's all about elastic collisions. We've talked about collisions before. where momentum is conserved. But elastic collisions are ones where we further define that the total kinetic energy is conserved. And that is what we take as the definition of an elastic collision. Right, so notice that's not a statement of energy conservation per se. It's just saying that there's no change in the total kinetic energy. Which, if you think of the work energy theorem, is just saying that there's no net work that's ultimately done during a collision. And the way you can kind of visualize this is you can imagine that it is possible for collisions to be elastic. Now I throw two blobs of clay at one another. They might come to rest, but that's not an elastic collision, because at the end of the day, you went from having non-zero kinetic energy of the two things that are moving toward each other, then they stick together and just come to rest. Well, there the kinetic energy has gone to zero. So that is not an elastic collision, even though momentum is still conserved in that case. If you define your system as the two blobs, momentum will be conserved, right? It's initially going in opposite directions, that it's equal and opposite perhaps. So then when they hit together, they stick together and there's no net motion. But that still is the same net momentum, which was zero in both cases. Momentum was conserved. Kinetic energy was not. So you can actually calculate that, right? Take two blobs of clay that collide with one another and come to rest initially. There was an ultimate change in kinetic energy. That means there ultimately was work done when two blobs of clay hit each other and came to rest. Where did that energy go? Well, in that case, it didn't go into potential energy or stay as kinetic energy, but it probably then turned into something like heat. Or it was the work that went into kind of deforming the object itself. That's still motion, forces being applied over a distance as these things move and compress. That energy then had to go into the work that's done when the thing kind of blobs up and takes its new shape. That is, just as an aside, that is the reason why the hood of your car is designed to kind of crinkle up when you get in a car accident. Because if you say run into a tree or drive straight into a tree, that tree is unlikely to budge. So if you hit the tree, your momentum can go into the tree because that's forces applied over time. Nothing needs to be moving there. So your momentum goes into the tree. But if the car and the tree are not moving, no work can be done in that case. So if work is how you change your kinetic energy, there's no way for your kinetic energy to go away if you run into a tree and nothing's moving. What happens then, so since something has to be moving for forces to do work, is that the hood of your car is designed to kind of crinkle up. So that crinkling, which requires things moving over distances, right, as they kind of crinkle up, that motion allows for the kinetic energy to be drained from your car, and ideally, of course, it goes into destroying your car rather than, say, work being done on you. But it's the same sort of thing. You go flying forward, that's why you have an airbag. An airbag allows a force to be done over a longer distance as you kind of sink into the airbag, compared to if you just slam your head into the steering wheel. That steering wheel is not moving, so your entire motion has to come to rest very quickly, which usually means, if you think of momentum, that means the average force on you is pretty high, which is why that's much more dangerous than if you hit an airbag, where the work, it can be done gradually, and then the average force on your face is much less than if you were to just smack into a steering wheel. But what about elastic collision? So if you had two balls, an elastic collision might be that they hit and then they bounce back, right, such that the total kinetic energy is the same before and after. You can imagine if you have something like a rubber ball or something that's very elastic, why are elastic collisions able to retain kinetic energy from pre-collision to post-collision? Well, the kinetic energy, of course, is not conserved during the collision because it gets turned into something else, because the things have to come to rest, and then their kinetic energy has to then go from zero to non-zero again as they move back away from one another. But if you think of it like a spring, right? An elastic collision means these things are very restorative, that if I compress it and let go, it returns to its initial shape, like spring, compared to a blob of clay where I squeeze it and it stays that shape. Springs are conservative forces. So if you have two things that smack into one another, as they press together, that deformation is like squeezing a spring in between them. That is turning the kinetic energy of these balls into potential energy that's in the spring. Potential energy, though, we can get back. So then as the things uncompress from one another, that spring turns back into kinetic energy, and they leave ultimately with the kinetic energy that they came in with, or leave such that the total kinetic energy has not changed. That's an elastic collision compared to an inelastic collision. The compression is spring-like. And in fact, most collisions in many ways, at least at the microscopic level, are like this, spring-like. You know, the world is just a wonderland of springs. You know, I run into the wall, I run into a table, right? There, you can think of them as surfaces that have exceptionally high spring constants, because they do deform a little bit, but then they oscillate, and as we'll talk about in a few modules, they are very highly damped oscillators, so they might oscillate a little bit, but then come to rest very quickly, because there's something that's kind of getting rid of that energy, some sort of friction or dissipation that usually ends up being heat. So that kind of is the conceptual idea. How might you solve for elastic collisions? How might you solve the equations? And it's actually not too bad, but the algebra is a little hairy. So suppose I have two balls. Let me do a simple example. Two balls of mass m, but this one has no initial velocity, but this one has some velocity, and it's moving that way. In this case, and I say that the collision is elastic. Now again, if I make my system the two balls, and assuming they're on a frictionless surface, momentum is conserved in the horizontal direction. So I expect, right, m v naught plus 0, the momentum before, to be whatever the momentum is after. So it might be mv1 for the left one, I'll say vl, and then mv right, whatever the momentum is for the right ball after the collision. Now let's have both balls be the same mass to make my life easier. And then since it's elastic, I can also say that the initial kinetic energy, which in this case is just 1/2 mv naught squared, better equal the kinetic energy of the system at the end. So these then are, I can ask, what do I know and what do I not know? I know v naught, I know m, but notice I could cancel all the m's, but I don't know these v's. And there are two variables I don't know, but that's okay because I have two equations with two unknowns. So I can algebraically solve for VL and VR. And it looks like once I cancel the m's, it looks like V naught equals VL plus VR, and V naught squared equals, so I multiply by m's, I multiply everything by 2, VL squared plus VR squared. Again, I'm taking V naught as a given. I could solve for VL and VR, right? I could substitute one of these into the other, solve for one, then yada yada. But since there's a quadratic involved here, notice that if you're solving for VL, you can imagine at some point you're going to have to take a square root. Square roots introduce plus and minuses into the expression. So while if you think back to cases where like we were solving for the tensions in strings, right, there's only one solution. When you have linear equations that have no squares or nonlinear terms, you only get one solution for all the variables. Now, since square roots are involved, right, you might imagine that there might be multiple solutions possible. Particularly, there'll be two possible solutions in this case, since these things are appearing as quadratics. So there ultimately are two possible solutions, which I'll let you kind of figure it out. One solution, you might think is kind of the boring solution, is that VL equals V naught and VR equals 0. So that's kind of not really a collision, but it is a solution to these collision equations where you had one ball kind of come in, but then after the collision, quote, that same ball just kept going. So it's as, right, it'd be a case where these two are my system and one just kind of moves past one another. You know, in that case, it conserves momentum and it conserves kinetic energy. That's one solution to these expressions. The other, which I'll let you solve, is that VL ends up being 0 and VR ends up being V naught, which is true, right? This results, the fact they have equal masses allows this to be the case. Else there would be some overall numbers in front if the masses were different. So in that case, when they're equal mass, right, one comes in, hits, and then the other leaves with the same exact velocity in the same direction. Momentum is conserved, right? There's always an m times v pointing that way. So it's always the same momentum before the collision and after the collision. And the kinetic energy is overall the same. It's 1/2 mv squared, either the v of this one or the v then of this one after the collision. And you might have done this in an intro physics momentum lab. You know, there's often maybe a collisions lab you can do where this is the case. Of course, the more interesting case is when you allow things to be more arbitrary. So there's some ball which I'll let it have big M, an initial V naught. Let's see, what do my notes have actually? I think I just have it as V. And then there's some other object which I'll give it a mass of little m, just to make that, so they could be different masses. And it might have some velocity, initial velocity, which is W, or omega. Now, of course, you might imagine there's a solution where, you know, they're moving and they never actually collide with one another. Or maybe this one's moving faster, so it's kind of something like this. That could still, even though there's kind of no interaction, that would still conserve momentum and would still conserve kinetic energy. Of course, the more interesting one is if there's, you know, if this one's moving faster, say, and then it kind of runs into it, or maybe they're moving, maybe one of these has a negative sign, so they're moving the opposite direction. I guess omega would need to have a negative sign, right? So they're moving towards one another and then collide. So if this were an elastic collision, and this is all 1D, I know that the momentum before better equal the momentum after, and I'll have some general variables, you know, V dash and omega dash as the post-collision velocities. And then, of course, if kinetic energy is conserved, then the kinetic energy before the collisions better equal the kinetic energy after the collision as well. And I can't cancel all the m's in this case. I can cancel all those 1/2s. But notice that, again, this is two equations with two unknowns, in that I know V and omega and M and N, or M and little m, and then I want to solve these for V dash and omega dash. So there is one solution, which is then that no collision actually occurs, right? V dash is just equal to V and omega dash is equal to omega. You can easily plug those in. It's kind of the trivial solution where the left-hand side will definitely then equal the right-hand side. So those are the cases where no actual collision really occurred in this case. The more interesting solution, just not too hard to solve for, but takes a little bit of work, is that you can write down what V dash and omega dash should be in terms of all the m's and the initial velocities. So let me write it down and I'll let you copy. Essentially, there's always a term that's multiplied by V, and then there's a term that's multiplied by the original omega. And the denominators are always the total mass. And hopefully my m's are distinct enough. Maybe I'll put the capital M in red so it's kind of clear which one is the capital M. There you go. So, I mean, it's an algebraic kind of, it's not too hard to solve for these algebraically, but you can figure these out, and those are kind of the algebraic expressions for collisions when they are elastic collisions. So maybe let me do kind of two kind of extreme examples just to make sure that this jives with our intuition. Let's let big M be much, much greater than little m, and also have little m's initial velocity be 0. So this might be the case that I throw a bowling ball at a marble, and the marble is just sitting there stationary, and I throw a bowling ball at the marble. What then is happening after the collision occurs? Well, we can try to intuit this out first. You know, you can imagine if I throw a bowling ball and there's a marble in the way, or go even more extreme, it would be a speck of dust that collides elastically with the bowling ball. You might imagine the bowling ball probably is not going to change very much in terms of what it's doing. So we might expect the velocity of the bowling ball to not change that much. However, that little marble suddenly gets a big smack on one side, so we might expect the marble to then go flying away. It at least has to be going as fast as the bowling ball, but you might imagine that if it gets that big of a kick, it might go flying ahead of the bowling ball too. Well, let's think. So let's first think of what the bowling ball's new velocity is when big M is greater than little m. So when you have expressions like big M minus m, right, because again, the first term is big M minus little m over big M plus little m v. Let me just focus on this term first and then come back to the other one. If big M is much, much bigger than little m, then that numerator is a very big number, right? Because essentially it's you have $1 million and you subtract a penny, right? So essentially you still have $1 million at the end of the day. So this top expression, I might imagine, actually let me put this off to the side because this is not the solution yet. So I might expect, you know, in this case, this is approximately, the numerator just becomes big M. The denominator also, right, you have $1 million plus a penny, you essentially still have $1 million in the denominator as well. So approximately both of those just become big M times V, or this entire thing just becomes V. Where the second term in the expression, right, where you have 2 little m over big M plus little m times omega, well there the numerator is staying, right, there's no big M in there, so it's just 2m. So you can't approximate that as anything because it's just 2m. So you just have to keep it as 2 little m. But then the denominator, again, you have the sum of the two, so this is approximately 2 little m over big M times omega. But we just said that big M is enormous, so that denominator is enormous compared to the numerator. So this is then going to be very, very small. Maybe you could say approximately 0. So then the bowling ball at the end of the day looks like its velocity is approximately unchanged. The bowling ball's velocity does not really change at the end of the day. And this is an approximation, of course, but the corrections are very, very small. Now what about omega? How does the marble's velocity ultimately change? Well, the first term you have is 2 big M plus little m times v. So that's going to approximately be, right, the denominator becomes just big M. The big M's cancel, so this looks like it's just going to be 2 big M over m times v, which is then just going to be 2v. And then the next term looks like it's m minus little m, big M, m plus little m times omega. Oh, but we said omega was 0, right? We said the initial velocity of the marble was 0, so this is just 0 anyway, regardless of what big M and little m are. So then it looks like the velocity of the marble then just becomes 2 times the velocity of the bowling ball. So yes, the bowling ball smacks into the marble, it goes flying ahead at twice the velocity of the bowling ball, and the bowling ball is more or less relatively unchanged as a result in these approximations. If you want to know how exactly they change, they do both, right? The bowling ball's velocity does change by a little bit, namely 2 little m over big M times omega. Oh, but I guess we said omega was 0 in this case too, so we should have said this was exactly 0 as well. Yeah, so the changes are very, very, very slight to the bowling ball. To the marble is extreme. And then what about the other case? Like, what if big M is much, much smaller than little m? And let's still stick with omega equals 0. So this might be like I throw a marble against a bowling ball, because now the marble is big M, which I'm saying is very small, actually. And then little m is the big mass in this case. So it might be I throw a marble against a bowling ball, or you could even go more extreme, since I'm saying omega 0, right? You throw a marble against a wall. If the wall wasn't attached to anything else, you know, would the wall start moving? Or let's just stick with marble and a bowling ball. I throw a marble against a bowling ball. Well, I'll let you figure it out. That then the marble in this case, when you make these approximations, ends up becoming negative little m over m times v. Because again, remember, little m is now the big one. So that ends up being negative v. So it comes in with v, hits the bowling ball, bounces back with negative v. And then what does the wall end up doing? Well, it ends up being 2 big M over little m times v. But since the denominator is huge in this case, this is approximately 0. Which kind of makes sense. I throw a bowling ball, I throw a marble against a bowling ball. As a result, the bowling ball really doesn't care, and the marble bounces back. So those are kind of examples of elastic collisions, and you can use those to play around with, you know, kind of the classic example is what if I drop 2 balls on top of one another, then the bottom one hits the ground, but then it rebounds and hits the one on top, and then what happens to the top one? That'll be a problem at the end of the video. And you can do that just by applying these kind of elastic collision equations, but then you apply it twice. All right, one more. Suppose I have a nail, and attached to that nail is a rope, which I pull horizontally straight out, and there's a mass of mass m attached to the rope. So essentially this, right? My hand is the nail, I pull it out, and then I'm going to ultimately let it go. You let it go, so you let go from rest. And let's have this thing have a length of 2r. That will be obvious in a second why I'm saying 2r. If you let it go from rest, and the rope was kind of taut to begin with, it should traverse out a circle as it falls down. And then falls down to when it's vertical, and then it would keep going. But then suppose there's another nail here that's halfway down. So this is kind of a length r, and so this is a length r. So there's another stationary nail. So that when the rope becomes completely vertical, it then runs into a nail that's halfway in between, and so then it starts to rotate around that nail instead. So instead of traversing this big old circle, it then might start to do something like that as a result. And the question is, when it hits the second nail, what is the angular velocity? Of m around that nail? So it's kind of sweeping out a big circle for a quarter of a circle, then it hits a nail, and then it starts traversing a smaller circle with half the radius. Does the ball start spinning around faster? Does the ball speed up? You know, what's going on when it hits that middle nail? So given that this is a bunch of circular motion, you might think that polar coordinates or angular momentum will play a role. And in this case, angular momentum is going to be helpful for us. Because you can think of that second nail as a collision that's happening. Essentially, it falls, but then when it falls, it collides with, it's kind of hard to do in real time, but it collides with a nail, or the rope collides with a nail that is present halfway down. So if I want to look at what's going on immediately after it hits the nail, I should say, what is the angular velocity of m around that nail immediately after it hits, the rope hits. Because of course then it will attempt to start doing circular motion, but it won't be uniform circular motion if it's all vertical. Could do this all horizontally, then it might be uniform circular motion. That might be easier. Why do the easy one when we can do the fun one? So, what might we say? Well, initially when the thing is falling during its quarter circle, it is feeling a tension from the rope. But again, if the rope was initially taut, then as the ball falls, it should stay swinging in a circle. Not uniform circular motion, but it will stay swinging in a circle. That means, if I use green for velocity, that means its velocity is always going to be perpendicular to the direction of the rope. The rope is always pulling towards the center of the circle, where the velocity is always going to be perpendicular to the direction of the rope. So in this case, then the rope does no work on the ball. Gravity, of course, is doing work. The thing speeds up as it falls. But the rope is not doing any work as long as it remains taut and is kind of stuck sweeping in a circle. That, of course, is not the case if I just drop this and ask, is the rope doing any work? You know, as it falls, the rope isn't taut, so there's no force being exerted. But then once it gets to the bottom and the rope becomes taut, obviously it's the rope that's slowing the thing down and then might eventually make it start moving back up. The rope is doing work in that case. But if it's constrained to kind of be doing circular motion, the rope is not doing any work on the ball. But gravity is, and there are no other forces in town, so it looks like energy is conserved. So we can at least apply energy conservation from when it goes from this kind of starting point to when it gets down to vertical right before it hits the nail. So T plus U start, I might say, is no kinetic energy, and then it's mg times 2r, maybe above the ground. If I define when it's vertical to be where, you know, if I make that my reference point, then if this is length 2r, right, it's a height 2r off the ground when it's horizontal. And then T plus U at the bottom, right before it hits the nail, we're going to have some kinetic energy. And then we're defining that to be where there's no potential energy. And these two better be equal to one another. So that looks like 2 mgr equals 1/2 mv squared plus 0. Looks like some m's cancel. I can multiply by 2. 4gr equals v squared, or v equals square root of 4gr, or 2 square root of g times r. Not too bad, just by, again, energy conservation in this case. Since gravity is the only thing doing work. So I know the velocity of the ball when it gets to this point, right? So it's moving this way with a velocity that's equal to 2 root gr. It then hits the nail and then starts to swing around the nail. I could ask, is angular momentum conserved, or can I figure out, and this is key, can I figure out a reference point to use such that if that's the case, angular momentum is conserved? And then how do I apply angular momentum conservation? So again, we have the nail, we have the top nail, and then this thing is moving to the right with some velocity v. And then it's going to start rotating around that center nail. So why not make that my origin? And then apply angular momentum conservation immediately before it hits that nail and immediately after it hits the nail from that origin that I've drawn in blue. Because again, if my system is not including the nail in this case, is just the rope and the mass, then there is a torque from gravity, but gravity is pointing straight down at this point. And so is r in this case, right? If I use that as my origin, then this is my position vector r. But then if gravity is also pointing straight down, r cross the gravitational force is going to be 0. So there's no torque happening from gravity. When it hits that nail, you can imagine that there's going to be a force from the nail on the rope pointing in this direction, right? F nail. But since I've put my origin at that nail, then r cross F nail is also 0 in that case. That nail can't be exerting a torque on the rope there, because I've conveniently put my origin at that location. So for this particular reference point, there is no torque coming from that nail. Then what about the top nail? Well, again, the position vector is here, and the nail is also exerting a kind of force, holding everything up. So the force from kind of the top nail is also going to be pointing straight up. That cross product is also going to vanish because they are, in this case, parallel instead of anti-parallel from one another. So at this point, immediately before and after the collision with the nail, there is no net external torque. I can apply angular momentum conservation with my origin being located here. So in this case, it looks like L is conserved. And again, using that as my origin, pre-post collision. So again, I'll stop with the vector, since this all is going to be angular momentum that is in or out of the page. What is the angular momentum before the collision? Well, I could write down from that particular rotation axis that, let's see, what are we doing? Well, I guess we can write down that the angular momentum, which again, angular momentum is just r cross momentum, or m r cross v. That from that particular origin, the position vector is pointing straight down, the velocity vector is pointing straight to the right. So they are perpendicular to one another, so there's no sine of angle between them. Or it's the sine of 90 degrees, which is 1. And it's going to be counterclockwise motion, which is positive. So it looks like this is going to be m times the length of the position vector, which is just r, times v at the bottom, which we said was 2 times the square root of g times r. So it looks like the initial angular momentum looks like it's 2m. Then if I pull the r inside, Looks like it's going to be something like the square root of g times r cubed if you want to lump all the r's together or something like that. Then there is the final angular momentum. And we could ask ourselves, well, one, we know it's conserved. So we should know we should be able to write it as m times r times v final. But the m hasn't changed and the r hasn't changed, of course. So why should the v change? The v doesn't change either, right? And again, if you think about it, if there's a nail kind of halfway in between, why should that kind of change at all what the ball is doing when it just hits the nail? The nail's not touching the ball, so why should the ball speed up or slow down when it hits the nail? It will ultimately start changing the motion that the ball takes, because it will start doing circular motion around a smaller circle. But at least pre and post collision, the velocity should not change. However, remember what we're trying to do is measure the angular velocity of the ball. So I could also write this as I times omega final, right, post collision. Where of course omega final is related to r and v. You might think that we didn't really have to do angular momentum conservation, but we still can. Now for a point particle, it's the mass of the particle times the square of the distance from the rotation axis. So that looks like it's just going to be m big R squared times omega final in this case. So in this case it looks like, and actually I think I'll take the r back out. So it looks like it's r root g times r, and that better equal m r squared omega final. One of these r's cancel. The m's cancel. And so then it looks like we get 2 square root of g times r all over r equals omega. But again, I could simplify this, and it looks like it's g divided by r all in the square root equals omega in this case, all with a factor of 2 out front. You could always convince yourself, right? Is this actually, does this have the right units? Well, it's the square root of meters per second squared, all divided by meters in the square root. So it looks like it's the square root of 1 over second squared. Square root of second squared is just 1 over seconds. Indeed, it has the right units of radians, which is one of those is and is not a unit, divided by seconds. So we have our angular velocity as a result, which was applied by angular momentum conservation. Now, let me quickly point out something, a common pitfall I feel that happens when you do this particular problem. That I know I definitely made this mistake when I did the problem earlier, of how you could inappropriately use angular momentum conservation. Right, so suppose you have this and you're thinking, well, okay, initially there's no angular momentum, but then it kind of gains some angular momentum about this rotation axis, and then when it hits, it switches to a new rotation axis and then starts flying around in a smaller circle. I'm going to do this all in red to emphasize that this is all wrong. You might say angular momentum is still conserved, but you might say the initial angular momentum is m times 2r times the final velocity. So you might take this as your origin, measure the angular momentum down here, which is 2r, it has some velocity, and then use that to do the initial angular momentum, but then say, oh, well, then the final angular momentum is m times just r times v nu, where in that case you're saying, okay, the rotation axis has changed, I'm going to measure now the angular momentum from the new nail, and it still has a mass m, but maybe its velocity has changed, in which case you might then say, well, then it looks like v new equals 2 v original. And so the velocity of the ball actually does double when it hits the second nail, and suddenly the ball is moving twice as fast as it curls around. This, again, all in red, all wrong. You cannot say that, obviously, because we just argued before that the velocity of the ball should not change. So what did you do here with angular momentum conservation that was incorrect? Well, you might be able to realize that you changed where you were measuring the angular momentum from before the collision and after the collision, right? It's wrong because pre-collision L naught was measured from the top nail. And then post-collision, L final was measured from the bottom nail. That is inappropriate because remember, angular momentum is defined with reference to a particular origin. So if you want to say angular momentum is conserved, you're saying it's conserved given a particular origin that you're looking at pre and post collision. The fact that you're switching the location of the origin pre and post collision is inappropriate. And this shows, how you can result in nonsense when you do that. Because since you changed the origin, the value of the angular momentum changed in that context. So you would not expect angular momentum to be exactly the same because you're doing two different problems on both sides of that equal sign. So again, remember that you have to use the same origin pre and post collision when you measure things from. So even though it starts kind of rotating around that top nail, you still have to measure everything from that mid nail if you want to then use that as pre-collision and then post-collision and apply angular momentum conservation. So always got to be careful with that pesky angular momentum conservation. All right, that does it.